तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, last time we went through the details and discussed the crystal structure of gallium arsenide. In fact, what we discussed for gallium arsenide holds good also for indium phosphide. That also has got zinc blende structure. Most of these 3,5 compounds have got zinc blende structure. So, wherever gallium was supposed to be sitting, you will have indium. Wherever arsenic was supposed to be sitting, you have phosphorus. Okay. So, general 3 and 5 elements are sitting there to form the zinc blende structure. Now, we saw the 1-1-1 plane, just putting it again, projecting it to you, okay, to see that you have got on the 1-1-1 plane all these are arsenic atoms, and this gallium atom is below that, because that is at A by 4, A by 4, A by 4 from this corner. So, that is below that, and this arsenic atom is even below that. So, which means as we go from along the 1-1-1 plane, you have got arsenic, gallium, arsenic, gallium. So, if you look at the entire wafer on one side, okay, of the 1-1-1 plane or 1-1-1 gallium arsenide wafer. If you take a gallium arsenide wafer, okay, you have gallium plane on one side, go on alternating, at the other extreme end you have the arsenic plane, because it can never remain arsenic on both sides. Starts with gallium, ends with arsenic on the other surface. Okay. So, general even for indium phosphide, you start with indium, other end of the 1-1-1 plane is phosphorus. So, sometimes to keep the general term, these 3-5 semiconductors, when you take 1-1-1 oriented wafer, you call it as 1-1-1A top plane or one surface, 1-1-1A and then 1-1-1B. These two have distinct characteristics. They are distinct characteristics because the 1-1-1A, the A phase, let me take the example of gallium arsenide, has got gallium atoms, which are having 3 valence electrons, which are forming 3 bonds down. They are attached to the crystal with the 3 bonds going down. So, out of the 3 valence electrons, all the 3 are occupying down. There is no electron available on the surface. What will be the implication of that? If there are no free electrons available, because all the 3 are busy forming the bond with the crystal, because there are no free electrons available, that surface is less reactive. Less reactive means it will oxidize slowly, it will etch also slowly, because for any chemical reaction there must be electrons. In the absence of that, all those reactions are slow. So, etch rate is slow, oxidation rate is slow in that 1-1-1 gallium plane or 1-1-1 A plane. If you go to 1-1-1 B plane, in the case of gallium arsenide, it is 1-1-1 arsenic plane. That plane has also got the out of the 5, 3 of them will be bonding into the crystal. Okay, if you look into the crystal structure, you will see it will be bonding into the wafer or the crystal from bottom 3 bonds, 3 electrons, but there are other 2 electrons which are there on the surface. At least one will be free for chemical reaction. So, the arsenic phase will be quick to react chemically, it will be quick to oxidize compared to the gallium plane or 1,1A plane. So, these are the two differences. It also reflects, this property also reflects on the ability to polish the two surfaces. Mechanical polishing or chemical polishing, whatever you want to do, when you polish the surface of the wafer, it is easy to polish 1,1,1B plane, that is arsenic plane, because it is more highly reactive. Whereas, the A plane, A phase, difficult to polish. So, if you ask a vendor, I want 1,1,1 gallium arsenide wafer with gallium surface polished, he will not get it. You will not get it. But if you say 1,1,1 arsenic phase polished, you will very easily get it, because it is easy to polish. These are some of the results, consequences of the peculiarity of the compound semiconductor. In silicon, it does not matter. Whether you take silicon, A top phase or bottom phase, 3 are bonding there, 1 is available for you for chemical reaction. So, whether you take top or bottom, it oxidizes the same way, you can polish both in the same way. These are some of the differences between the crucial or major differences, apart from the crystal structure, the reactivity of the surfaces. Now, let us take a look at further, having seen these structures and differences. We also saw the cleavage plane of 3,5 compounds, particularly gallium arsenide, indium phosphide, etc., are 1,1,0 plane. That also we explained why. Let us go further down. Having seen the crystal structure, we would like to see how to make devices. And to make devices, you must have the ability to dope them. You should be able to make p-n junctions. You must be able to make p-type material. It is not enough if you have a gallium arsenide crystal, you must be able to make p-type gallium arsenide, n-type gallium arsenide. So, dopants or impurities in 3,5 compounds. I will take the example of gallium arsenide. What I discuss holds good for indium phosphide also, because they go hand in hand, they compete with each other for microelectronics and also optoelectronics. Now, in this gallium arsenide, gallium is from 3rd group, arsenic is from 5th group. Now, if you take impurities from the group 2 from the periodic table, impurities from the group 2 are zinc, cadmium, beryllium, magnesium. If you take any one of them, if they are occupying the gallium site, what will happen? In the gallium site, it calls for 3 electrons, because gallium has 3 valence electrons. It forms covalent bond with arsenic with 5 electrons from arsenic, 3 electrons from gallium. So, totally 8 to form the covalent bond. Now, if you put zinc and if it is occupying the gallium site, zinc is from the 2nd group, it has only 2 electrons. So, when it is sitting on the arsenic gallium site, there is one deficient 1 electron, that is, there is one vacancy. So, it becomes p-type material. Absence of electrons, you say it is a hole, that is equivalent of having a plus charge. So, that is actually p-type. Now, the numbers here are the numbers which tell you where that acceptor level is with respect to the valence band. After all, you would like to see, you would like to see how much is what is the ionization energy. For example, the vacancy, you can call it as a hole, if that hole has to move from the vacancy to the valence band. How is it possible? By transfer of electrons from the valence band to that point. That vacancy can be occupied by transferring electrons from the valence band to that point. That will be negatively charged when it is ionized. So, the energy required to ionize that acceptor level is the ionization energy. Now, it can be easily ionized if it is close to the valence band. Now, this is about 31 millielectron volts. Gallium arsenide band gap is 1.43 electron volts. Out of that, 31 millielectron, very small, very close to the valence band. That is why E A is the acceptor level, E V is the just for clarifying what I am implying, E C E V, that is the band gap. Now, what we are telling is you have this acceptor level, or this when you introduce zinc or cadmium or beryllium, that introduces a level. This is actually the ionization energy required to transfer electrons from here to here. In other words, to transfer the vacancy from here to here. That vacancy, when electron moves from here, you have a plus charge there. That is that plus charge which is available for current transport. Okay. So, this is that what we are talking of, and this is the p type. Okay. E A is due to any one of them, zinc, mostly it is zinc that is used, okay. And today people are using beryllium. In fact, if you see on this table, we have given some of the concentrations which are achieved, which have been achieved. For example, zinc can be introduced with a concentration of 10 to the power of 21. That means you can make P plus gallium arsenide. P plus means very heavily doped p type material. P plus gallium arsenide by introducing zinc to a level of 10 to the power 21. Beryllium, you can go beyond 10 to the power 19, but actually upper limit I do not have. These two, there are no numbers are available at the moment, implying these can be used, but there are difficulties in realizing them, using them. So, mostly zinc and beryllium. In fact, if you open up literature, the most popular p type dopant in gallium arsenide, indium phosphide is zinc. Zinc doped gallium arsenide. Okay. You can adjust the doping concentration. Now, on an average, that energy difference is about 40 million milli electron volts, which is almost similar to that of silicon. Silicon also, if you introduce boron, which is third group element, silicon is fourth group. So, one less electron in boron, it introduces a level similar to level at about 40 to 50 milli electron volts. Let us take a look at the N type impurities. N type impurities are the p type. Introduces a level E D, donor level, E C E V. Okay. That is supposed to donate an electron to the conduction band. That means, when it ionizes, which should be possible even at room temperature. If you should be able to ionize a donor even at room temperature, the implication is with very small energy, the donor should donate electron to the conduction band. Okay. That means, the donor level is located very close to conduction band, if it should donate. That is the meaning of that. So, you put it as, what is the meaning of this plus? The meaning of the plus is, when it has donated an electron, it is like this, a donor atom with an electron attached to that. Okay. And donor in the case of silicon is from the fifth group. So, the fifth electron donates, because it requires only 4 to form the covalent bond. Now, if you take sixth group, in the case of gallium arsenide, okay, if you take sixth group element, it has 6 valence electrons. If it is sitting in the arsenic site, on the arsenic side, there is 1 extra electron. Arsenic site requires 5 electrons, because it has 5 electrons. Now, if instead of that, if fixed group element like sulfur, selenium, tellurium, all of them belong to fixed group. If they are occupying the arsenic site, then there is one extra electron is there, which is very loosely attached, because all other 5 electrons will be forming the bond. So, those are the one which form the bond. So, the 5th one is available, that will be donated to that. So, this one once it goes up, once it is donated to the conduction band, it is left with the positive charge. So, that is why we put that donor level as plus there, implying it is ionized. What is ionization energy? Energy required for the electron to move from the donor level, that is this ED, that is ED to the conduction band, and that now notice the difference. This is one of the things that we should note. EC minus ED, 6.1 milli electron volts. That is the one of the major differences between silicon donors and donors in silicon and donor in gallium arsenide. In silicon, it is something like 40 to 50 milli electron volts. Gallium arsenide, these ionization energies of donors, shallow donors, are 6.1, 5.9, 5.8, on an average 5 milli electron volts, very small. They are virtually very close to conduction band. What is the consequence of this? The consequence of that is, you go down below room temperature, there is no carrier freeze out. Okay. If you take silicon for example, it requires certain energy of 50 milli electron volts for donating the electrons. Okay. You go down below room temperature, you would have you will see, or you would have calculated in some places, that as you go down in temperature, number of donors which are ionized, that decreases. You go to much lower degree temperatures, less and less number of them are donated. What does it mean? That means the electron concentration goes down, it is frozen into the donor atom itself. It is not moving there, it is right here. That is what we say, imply when we say it is frozen. If you take gallium arsenide, the energy is 6 milli electron volts or 5 milli electron volts. Then, even if you go down to liquid nitrogen temperature, even if you go down to that temperature, the electrons do not remain there, they are available for conduction, because very little energy is sufficient to release those electrons to the conduction band. So, even at much lower temperatures, you have these electrons which are available for conduction. Whereas, in the case of silicon, you go down to much lower temperatures, liquid nitrogen, etc., the number of electrons which are available will be coming down, drastically reduced. So, the conductivity goes down, and if it is delivering certain current at room temperature, at lower temperatures, the device will not be able to deliver that much current, whereas here it can work. You can immediately see what will be the benefit of this. The benefit of this is, you can make use of gallium arsenide devices at lower temperatures very comfortably. Now, if you recall what we discussed earlier, you would like to operate some of the devices at lower temperatures to avoid scattering by the, or to reduce the lattice scattering. Okay. So, if you go down to lower temperature, if the electron concentration is reducing, no point. Where is the question of scattering? There are electrons available for conduction. So, this is one of the advantages. You are cutting down lattice scattering by going to lower temperature. Okay. Now, of course, you will have be worrying, what about ionized impurity scattering? We have got methods of separating the donor and acceptor to prevent the ionized impurity scattering. That we will discuss when we go to high electron mobility transistor discussion. Okay, now, so main impurity that is used is sulfur. Okay. Selenium and tellurium are used. You will see selenium doped or tellurium doped gallium arsenide. You try to avoid that because it forms some compounds. See, after all, if you introduce tellurium, it should remain as tellurium so that it acts as a donor there. If it is making a compound like tellurium, gallium telluride, like this, it is no longer a donor, it is a unwanted lump standing there in gallium arsenide's way. So, it is no use. So, that is why they find difficulty in that, but still when the doping concentration is low you can use that, but when it is higher you must use sulfur. There are better impurities, we will go back to that, go and see those things afterwards. After seeing what could be this reason for this low ionization energy, explanation for that, because after all we would like to see why it is so low compared to silicon. If you recall, when you discussed the silicon ionization energy, there is a simple model for this. The simple model is the fifth group impurity in silicon, okay, may be represented by a nucleus with a single orbiting electron. I am just fifth group when you say it is in silicon. If you take gallium arsenide, it is sixth group sitting on the arsenic side. Okay. So, what you are telling is a donor. The donor, shallow donor, can be represented by means of a nucleus with a single orbiting electron, like that. Okay. This is the one which is orbiting. This is equivalent to a hydrogen atom, hydrogen like in character, which has got one electron which is orbiting. Now, there you consider, you find out what is the ionization energy of that electron. There what you mean is the energy required to remove it from the vacuum level. That is calculated by this formula. Okay. Once you consider a hydrogen atom, what is the ionization energy of the electron, energy required to remove the electron away, that is used by this formula. Okay. This is almost dealt at the high school level, let me not go into that, where here m naught is the mass of the electron. When you talk of hydrogen, you will talk of the free mass of the electron, and q is of course the charge. N is 1 depending upon energy level. If you talk of, when you talk of hydrogen atom, the electron, that is N is 1, only one electron. H is Planck's constant, epsilon is permittivity of free space. So, when you use that, it so turns out that substitute for m naught h n equal to 1, epsilon 0 is 8.854, okay. Epsilon 0 is 8.854 into 10 to the power of minus 14 farads per centimeter. Okay. M naught is the mass, you do not have to know what it is right now, okay, because that substitute that, it is very small. H is Planck's constant. H is Planck's constant. Substitute all that, this turns out to be 13.6 electron volts. Okay. So, that turns out to be 13.6 electron volts. Now, when you consider the silicon atom or gallium arsenide atom, or for that matter indium phosphide atom with the donor or a donor in these materials, when you consider it as just like a hydrogen like atom. So, if you want to compute the ionization energy of the donor, what you do is you compute this quantity, because after all when it goes to conduction band, it is available for free transport, it is freed from the donor, it is available. So, that is the ionization energy. Now, what should you do to compute that? And you can put it as 1, and m naught you replace by the effective mass, because the electron now is in a crystal. The way the electron moves in a crystal is different from the way it would move in the free space, because an electron moves under the action of a force, external force, okay, plus it experiences the force within the lattice itself. Okay. Within the lattice itself, there are electrostatic forces which are acting on that, internal forces. So, the way it moves is different. So, people have simplified the whole thing, so that you can apply Newton's laws of force. Force is equal to mass into acceleration, and that force is actually the applied force, and the mass is the mass of the free space, free electron, if it is free space. So, for a given force, it will accelerate decided by the mass. Now, if that electron is moving within a crystal where other forces also come, if those forces are already aiding the movement, for a given force, okay, there will be different acceleration. So, you can still apply the Newton's laws of force, the force equal to mass into acceleration. Okay. The F is actually what you see outside is the applied force, but the electron experiences a mass, experiences a force which is a combined effect of external force and internal force. So, to accommodate that internal force, still use force is equal to mass into acceleration, you use a different mass, that is called effective mass. It will look as if the mass is different. Normally, if the mass is m naught, when I apply a force F, acceleration is force divided by mass. Now, when I apply the same force, if the acceleration is more, it appears as if mass is smaller. So, that is effective mass. That is because in addition to the applied force, there is internal force that is coming in. So, acceleration is more. Still, you can apply Newton's laws of force to use the effective mass concept. So, now, what you should do here is replace that m naught by effective mass. People have computed that, and then this epsilon 0 you replace by epsilon r epsilon 0, where epsilon r is the relative dielectric constant. That is what is put here. Epsilon r for gallium arsenide is 12.8, and Mn star, effective mass of electron divided by actual mass of electron, is 0.067. Okay, you can see it looks as if it is much lighter, which can tell you that if you apply a force, the electrons will run virtually much faster than in the free space, because there are additional forces internally. A mass of hole, okay, let me not get into the physics of this, we borrow this result straight away. The mass of effective mass of holes divided by effective mass of electron or is 0.5. It is not as light as electron. So, now ionization energy, now what you do is, just I will go back once, replace m naught by mn star. That means, what I should do is, whatever I get here is 13.6 divided by m naught multiplied by mn star, or what I do is 13.6 is there, divided by m naught multiplied by mn star. It works out to our convenience. I do not have to know what is the actual mass of electron. All that I have to know is what is mn star by m naught. Okay. That ratio, which is much smaller, divided by, in the place of epsilon 0 square, you have epsilon r also coming up. So, that is that. So, this number when you evaluate, it is 5.56 electron volts, milli electron volts. So, the ionization energy turns out to be very small, because the effective mass of electrons is very small. Whereas, the effective mass of holes, if you see, E A minus E V, is much larger than that, because that is m p star by m naught is 0.5 for gallium arsenide, m n star by m naught is 0.067. So, depending upon how small is the effective mass, you get smaller this energy. This model is a very simplified model, but it works out. It is amazing. Okay. A hydrogen like model can be applied to such a complicated structure, crystal. Okay. Now, so this is the thing. Now, you can see the whole lot of them you can see. I hope this is clear enough. Exactly all that you do is 13.6, you multiply mn star by m naught, divide by epsilon r square. The entire ionization energy depends upon that ratio of the effective mass to the actual mass. Oh. Now, using that, if you sum up and see, gallium arsenide indium phosphide gallium nitride I have listed here, because these are the first two are the very popular ones. This is the one which is finding its way in the gallium nitride. So, I have just added that also, and they are all almost comparable. Okay, they are almost comparable here, these things. What are not comparable are, or varying are, effective mass of electron 0.067 for gallium arsenide, 0.077 for indium phosphide. In fact, this also decides what some mobility is. Okay, if mass is smaller, the mobility is better. Okay. So, you can see from here that mobility of electrons in gallium arsenide will be higher than that of indium phosphide, and that will be higher than that of gallium nitride. It is true, 8500, 4500, 2000, that way it goes. Now, MP star by M naught almost 0.5, 0.6. So, that is why this ionization energy, whether you take of silicon, gallium arsenide, indium phosphide, they are almost same, 40 to 50 millielectron volts. Whereas, if you take the ionization energy of donors, silicon it is about 0.5. I have not put it there, because it is much larger than that of gallium arsenide, etc., at least 5 to 6 times. So, that is why this is larger, and in the case of gallium arsenide, indium phosphide, that is small. Okay, that is a model to see what actually is the cause for this. The cause is the lower effective mass, which is decided by several physical phenomena happening within the crystal itself. Okay, now we have discussed the donors from the 6th group sitting on the arsenic side, acceptors from the 2nd group, okay, 2nd group elements sitting on the gallium side forming acceptors, elements from 6th group sitting on the arsenic side forming donors. What about the 4th group elements? Okay, they are amphoteric. Amphoteric meaning it can go either way. It is the greatest opportunist, because it has got a chance if it can go and sit in the gallium side. Okay. If it give a chance, it will go and sit in the arsenic side. What is the meaning of given a chance? When they say given a chance, you give a vacancy there, it will go and occupy that position, gallium. To give a vacancy on the arsenic side, it will go and occupy there. That is why it becomes amphoteric, either way it can go. If it occupies the gallium side, what does it behave? If silicon 4th group sitting in the gallium side behaves like a donor, 1 extra electron, where you require 3, you have got 4th group element. If it is sitting on the arsenic side, it is actually acceptor, because 1 less electron. You need 5 electrons, whereas silicon has only 4. So, you can become either p type or n type, but it so turns out it has some sort of choice. It prefers to go act as a donor, and when the state acting as donor, what you mean is silicon prefers to go to gallium side, unless you create special situations where arsenic vacancies are tremendously more. Normally at room temperature itself there will be vacancies. If you raise the temperature, the vacancy concentration will go up. So, given any particular condition, crystal growth, there will be vacancies, both gallium and arsenic. When they are more or less comparable numbers, it will go and occupy gallium side. I just deliberately put this table, just sort of theorized or observed certain pattern. Okay. See here, silicon, germanium, tin, lead, all these belong to 4th group. All of them in gallium arsenide act as donors. When I say when I act as donors under normal conditions, unless you create additional vacancies in arsenic, when there are both arsenic and gallium vacancies present in comparable numbers, it will become donor. The reason, this is the table which I have put just for, it is a hunch, it is just an observation that I have made. I do not see it actually mentioned in books, but generally you can see gallium radius of the gallium atom, tetrahedral radius of gallium atom is 1.26 angstroms. About arsenic, that is 1.18 angstroms. So, in gallium arsenide, if you have vacancy of gallium, that vacancy site is slightly bigger. Okay, this is a physical phenomena which you can observe, whereas vacancy site of arsenic is slightly smaller. So, if a foreign atom or if a guest is coming and sitting, the guest atom will come and occupy where it feels comfortable. It will feel comfortable if the vacancy site is bigger. Okay. This is a law of the nature. So, observing that gallium vacancy is bigger than arsenic vacancy, because gallium has bigger atom size, that becomes donor. Now, you may ask, you are flouting the rules, there is one atom here, carbon, it actually generally becomes acceptor. Now, the carbon is a small atom, okay. Tetrahedral radius you can see 0.77. So, it will go either way. It so turns out that again you can see the law of the nature. A small fellow, if there are bigger seats are there, would tend to occupy which is a smaller one. This is just on a lighter sense. Okay. So, you can see the carbon is occupying that arsenic site and act as an acceptor. It does not mean that it does not go to the gallium site, it also goes, but most of them tend to go and occupy that. There will be other criterion like electronegativity, etc. But generally this is a reason. Now, let us take a look at what we say, how far is it true. Take a look at gallium antimonide. Gallium 1.26, antimony 1.36. Gallium is bigger. Now, all these atoms will tend to go into the bigger vacancy, that is antimony, all acceptors, and N is neutral, means it maybe it goes either way, goes into both. So, that is rather you do not see the effect of that. People have not been able to observe very clearly about lead, maybe lead on gallium antimonide. Similarly, you can see indium arsenide, which is bigger. From here itself you can see it is indium. Indium is 1.4485, indium atom is 1. Bigger, much bigger than gallium, 1.44, and arsenic is 1.18. So, it goes and sits in the indium site. This is just a curiosity, I just made this table to see whether something tangible is there, and it seems to hold good like that. And of course, this one is neutral, implying it goes either way. In fact, lead is quite big. So, that is why it does not matter where it goes. Between the two of them, that is the what we are seeing is indium arsenide. Indium is 1.44, same as almost, okay, it is smaller than that. So, it probably tries to squeeze in both indium and indium arsenide, okay, generally. But what I am pointing out is general law. Similarly, indium antimonide also is generally follows similar rules, slight flouting of the rules is there. This is just an observation. Okay. So, now if you put silicon into gallium arsenide, keep on adding silicon into while growing gallium arsenide, keep on adding silicon into that melt. What happens is the carrier concentration becomes equal to silicon concentration. For example, 10 to the power of 17 silicon atoms in gallium arsenide will go and occupy the gallium site, which is bigger than silicon. Silicon is 1.18 angstroms. Okay. So, both are same. 10 to the power 18 is almost linear. 10 to the power 19 start deviating from, it is not 10 to the power 19, it is smaller than that. So, as you go to higher and higher silicon concentration, the electron concentration does not increase linearly, it is sublinear. Reason? As you go on dumping more and more silicon, they prefer to go to gallium site, but as you go beyond certain level, they start finding that there are arsenic sites also, they can go into that, because they are getting filled up. The gallium vacancies, it starts getting into arsenic side. So, what happens? From 10 to the power of 18 or 10 to the power 19, around that, as you go, if you go beyond this point, the additional silicon atoms do not go into gallium side. Many of them tend to go to arsenic side. So, the electron concentration does not increase linearly, it becomes sublinear, and beyond a certain point saturates, because beyond that point it goes equally okay, both into the gallium and arsenic side. So, if you introduce them equally, you have got one shallow donor, one acceptor, one donating, one accepting. So, there is no contribution, that is why the electron concentration saturates out beyond that point. Now, just few examples where you can see tin follows the same rule. It can go either way and it becomes n type, but there is a donor, the fourth group tin sitting in the third group site, gallium site, and it becomes nonlinear after some time. Okay, that is exactly like the case of silicon. That is what we mean by that. So, tin also behaves in sublinearly, implying tin is located in both gallium and arsenic sites as you increase the concentration. All right. Now, just 1 minute. Yeah. Now, what I am trying to point out is, going back to silicon, we said silicon prefers to go and occupy gallium site and become donor. Now, that is under normal circumstances, but when you grow the crystal by a method known as liquid phase epitaxy, okay, then what happens is, maybe I have to draw the diagram, I will just go through these statements first. See what happens. Liquid phase epitaxy, LPE, I take a silicon gallium arsenide substrate, okay, and then I try to grow gallium arsenide layer on that with some silicon doping. Silicon even will come from contaminants. So, with that, when I do, what happens is, at lower temperature it gives p type gallium arsenide. I have some gallium arsenide substrate. This may be undoped. It is a substrate that I am using. On that, I want to grow another layer. Like that. This is a layer which I am growing, epitaxial layer. Maybe it is not visible, I will just redraw that. That is epitaxial layer. Epi is arranged upon, you arrange atoms on the top of that. So, this can be done by different ways. In fact, we will have occasion to see in some detail immediately after these dopants etc. in the next 1 or 2 lectures. So, this layer when you grow, what you can do is keep this gallium arsenide substrate in contact with the liquid of gallium arsenide. Okay. Let me draw that diagram for the completeness sake here. Let me put it down here separately. If you take a look at the gallium arsenide phase diagram. I am drawing into metallurgy now. Okay, if you take a look at that, and if I take temperature, okay. Now, if I take a look at that, the phase diagram is like this. It tells you the phase of liquid, gas or solid of the material that is existing at different temperature. So, if you draw, this is a composition. Here it is totally gallium, here it is totally arsenic. I can move, it is gallium arsenide. Gallium rich gallium arsenide, arsenic rich gallium arsenide, and here stoichiometric gallium arsenide. Truly, okay. Now, if you take a look at that, I will draw a line like this here. This line, this is important because all those people who talk of gallium arsenide, indium phosphate will talk of this phase diagram. Now, what does it tell you? I have a line here at 29.75 degrees centigrade. What is at 29.5 degrees centigrade? Melting point of gallium. That means in Chennai, if you take gallium, it will be liquid, because it is never below 29 degrees centigrade. Maybe even in this room may be cooler, but otherwise it will just like a mercury it will look like. And if you take arsenic, its melting point is somewhere here, 810 degrees centigrade. Okay, 810 degrees centigrade. That it is volatile at that temperature. If you take gallium arsenide, what is the melting point? Very easy to remember. Silicon, you know, it is 1410 degrees centigrade. Gallium arsenide 1234, 1234 plus 4, 1238. So, remembering is easy. Yeah, what is the melting point of gallium arsenide? 1234 plus 4, that is 1238. So, you take that. See, phase diagram will give you the melting point here, 1, 2, 3, 8. 1, 2, 3, 8 degrees centigrade. So, this is the melting point here, that is the melting point there, this is the melting point. In fact, draw those lines together, draw those things together like this, roughly. What is that line? This is liquid, this is solid, liquid plus solid, okay, this is solid and that is solid. Okay. You have liquidous line, below that it will be liquid plus solid, will coexist, and finally it will be solid here. Okay. Now, you will have, as you move from here to here, you will have, for example, if you come down from here, freeze from here, you will have, this is solid actually, this whole thing in this phase diagram is solid. Telling you, you will get gallium arsenide. If you freeze from melting point, you will get solid gallium arsenide stoichiometric. Okay. Now, in the liquid phase epitaxy, what you do is, you freeze somewhere here, you freeze, take this gallium arsenide, keep it in contact with the liquid, slightly reduce the temperature. When you start reducing the temperature, that is the liquid phase epitaxy, the composition from here will start freezing out, crystallizing and staying on that. It is a very interesting thing. If I go across to Anna University, they will do this liquid phase epitaxy for gallium arsenide. We do not do it in IIT Chennai at Madras. Okay. So, this is the method. You freeze it, okay. You will get liquid plus solid, solid in contact with that, and the solid will settle on that. Long time it will take, and the freezing solid has a composition decided by this. If you just freeze here, the composition of the solid is decided by that. And this has relevance to what we are talking of here. Why it becomes p type, why it becomes n type. Okay. Now, if you expand this portion, if I expand this portion, okay, this portion alone, if I expand, this is not a single line. This is called congruent transformation from here to here. That is just suddenly from liquid to solid. Whereas here, liquid plus solid. Here it's only solid totally. See, we have deviated from electrical engineering, physics, everything gone into metallurgy totally. Okay. So, but this is important to understand some of these things what are happening. So, if you see that, what happens is, okay, you have that line what we saw is something like this, something like that. This is that line, and this is 0.5 gallium, 0.5 arsenic. Are you able to? Okay, this is stoichiometric. Stoichiometric gallium arsenide means 50% gallium, 50% arsenic. That is how the stoichiometric is. If you come away from that, if I come down from this side, what happens? This is 50% gallium, 50% arsenic. 0 arsenic, full gallium. If I come here, it is gallium rich, arsenic deficient. When you say gallium arsenide with gallium rich but less arsenic, what does it mean? There are arsenic vacancies. This is another way of telling gallium rich means arsenic vacancy. Okay. One is rich, other one is poor automatically. Okay. So, arsenic vacancy is present. So, if I freeze from here to here onto this point here, and the freezing solid has got that composition, means I am coming down to this side. And what is here? Gallium rich. That means arsenic vacancy is present. And if arsenic vacancy is present, the silicon contaminated unwanted silicon or silicon if you are introduced along with that liquid, if you have introduced silicon, that silicon will go and sit in arsenic vacancy, that is p type. Go to higher temperature right up to this point, then I am putting it to expand it here. It freezing compound has got that composition. What is that composition? Is it arsenic rich or gallium rich? It is arsenic rich, because this is a 50% point, that is arsenic rich. That means gallium vacancy, less arsenic, gallium vacancy, which means it goes and sits in the gallium vacancy. See, now you have forced a situation where either you have got arsenic vacancy or a gallium vacancy. If there is gallium vacancy, you get high temperature n type. So, what we are trying to tell is relative vacancy concentration depends upon the growth temperature and arsenic overpressure. So, depending upon the relative vacancy concentration, you can make p type or n type. This is one of the approaches people used to make some of the p-n junctions by just by varying temperature. You grow up to certain depth at that temperature, suddenly jack up the temperature quickly to that, you will get n type. So, you can get a p-n junction. In fact, light emitting diodes of that nature can be made. You can get very high pure material with liquid phase epitaxy. So, this is one of the advantages, and this tells you that it is not necessary that silicon will go and make n type only in gallium arsenide. it will also make p and n depending upon the opportunity. That is why I said it is an opportunist. You give an opportunity, it will grab it. Here you are giving an opportunity of gallium vacancies or arsenic vacancies, you get p type or n type. So, this is the situation that you have got with the thing. So, that is actually as far as the impurities are concerned. So, today what we have done is we have talked about the p type impurities and n type impurities. In gallium arsenide, same impurities will be p type and n type in indium phosphide. In fact, even when we go to gallium nitride, you will see silicon can be used for doping gallium nitride. Okay. So, impurities are same type, and also we have seen, I am summing up what we have said today, we have seen that the ionization energy of donors is very small in the case of gallium arsenide, indium phosphide, etc., but will not be as small in the case of gallium nitride because effective mass is not so low. So, because of this, it is very easy to use these materials at low temperatures, because there is no carrier freeze out. This is one of the key things that one should remember. This is n type. What about p type? We are not concerned about p type and p type for making FETs, etc., because p type is no use in switching over to gallium arsenide, because gallium arsenide mobility is, whole mobility is not better. So, you talk of only the devices which deal with the electron transport. So, that is why you talk of that type of impurities. Now, tomorrow in next lecture we will just discuss some other impurities which have been very popular for realizing semi-insulating gallium arsenide, because semi-insulating gallium arsenide is important for making integrated circuits. That we will see in our next lecture.